Okay, so here is just an example comparison distribution. Okay, so say this is for a z-test. It has a mean of 5 and a standard deviation of 1. We have seen in hypothesis testing that we could go and plot the sample mean on the comparison distribution, right? Maybe we have a sample mean raw score of 7, okay? And that works out to be as the z-score of 2 in this distribution, okay? So that's our sample mean, z-score of 2. The p-value for any situation is always the percent of scores that exceed the sample mean on the comparison distribution. Okay, so this area here in orange, if we went to look that up, that is the p-value. Okay, it stands for probability value. And again, it's just, so it's the percent of scores that fall at or above the sample mean on the comparison distribution. And you could also, it's probability value because you could interpret it as the probability of randomly drawing a score this high or higher from this distribution. Okay, so this area here, that's what we call the p-value, and we can go and look that up in the normal curve table, right? If we wanted to get the percent of scores at or above a z-score of 2, then we would go to the normal curve table, and we're going to look up a z of 2 and then find the percent in tail. So we could go and do that. So here's z-scores all the way down to 2. Okay, percent in tail there is 2.28. So the p-value then is 2.28, which means that only 2.28% of the time would a sample mean this high or higher be drawn from this distribution. Because the comparison distribution represents the null situation, another way you could think about the p-value is that you could say in a null situation, you would only expect to get a sample mean this high or higher 2.28% of the time, okay? Remember that the nature of hypothesis testing is that you reject the null and have support for your research hypothesis if it would be unlikely to obtain your sample mean in the null situation. So this is the null situation, and you reject the null if you get an unlikely sample mean from this distribution, right? So we want an unlikely sample mean to reject the null. We talked about how the significance level that we set is how we formally define what an unlikely sample mean is. What an unlikely mean is in the null situation. And usually we set it to either 5% or 1%. So if in your test you have set a significance level of 5%, any sample mean with a p-value less than 5%, it meets the criteria of an unlikely sample score in the null situation. So it meets the unlikely score criteria, and therefore you reject the null. So really, all you need to decide whether or not to reject the null is you need a p-value for your sample score, and you need to know the significance level. And if the p-value is less than your significance level, and I'm just going to remind you, we often call that alpha. If it's less than alpha, then you reject the null. Or in other words, you say results are significant. But if P is greater than your significance level, then the likelihood of getting a sample score in the null situation is too high based on what you've defined as a low likelihood event. So if the probability is greater than the significance level, right, what you've set as defining an unlikely event, then you do not reject the null. And you'd say results are not significant. So this is actually kind of a much more simple and straightforward way of doing hypothesis testing, where all you need is the p-value and the significance level, and you're just comparing them. And so the beauty of doing this in Jamovi is that that's all you really need. So p-value, you are never going to have to calculate it. Jamovi gives this to you in the output, and I'll show you that in a couple minutes. And then your significance level, you should be told this in the problem. For this class anyhow, or if you're if you're a researcher, you kind of decide whether your significance level is 5% or 1%. So yeah, it's a much faster and more straightforward way of making the decision of whether to reject the null.